Next to the last section, section 6.6. So we're still in chapter 6, analytic geometry, and we're going to talk about the polar equations of conics in this section. So we're going to analyze and graph polar equations of conics. And I'm not going to ask you to memorize these. I'll give you the table, and I want you to know how to use the table and draw the graphs. So you're going to also want to be able to convert the polar equation of a conic to a rectangular equation. So first we're going to analyze and graph polar equations of conics. So they're going to have r's and thetas instead of x's and y's. So if we use a polar description of the conic sections, we get a single expression for all the three conic sections we have studied. Pretty amazing. So here's the definition. Let capital D be some fixed line called the directrix. So we talked about directrix with parabola, but it turns out there's also a directrix with the ellipse and the hyperbola. We just don't talk about them when we're talking about the rectangular form. So then let F be some fixed point called the focus. And we did talk about the focus in each of the three: parabola, ellipse, hyperbola. And this focus needs to not be on D or you get a degenerate conic. Then let this little e is not the e from logarithms. It's just a letter e that's called the eccentricity, or you'll also hear it said eccentricity. So if you have a perfect circle, the eccentricity is 0. And then the more squashed the circle is, the less it's like a circle, then the eccentricity changes. So let's look at how the eccentricity is defined. So it's a set of points again, set of points P, such that, sorry about this typo, the ratio of the distance from the focus to P, the point on the shape, divided by the distance from the directrix to the point P on the shape, equals a number, small e, that's called the eccentricity. So if e equals 1, then the conic is a parabola, because we looked at the fact that on a parabola, every point on the parabola was equal distant from the focus and from the directrix. If e is smaller than 1, the conic is an ellipse. So the distance from the focus to the shape is smaller than the distance to the directrix, and that makes the shape close up and become an ellipse. Then if e is greater than 1, the shape opens out and becomes a hyperbola. So I'll show you an interactive figure on Wednesday to help make that clearer. For both an ellipse and a hyperbola, the eccentricity satisfies this equation, E equals c over a. C is the distance from the center to a focus. So this is consistent with what we've been doing. C from focus to center. And A is the distance from the center to a vertex. Okay, so on the ellipse, the distance from the center to a vertex is this distance. And on a hyperbola, here's the vertex, here's the center. It's this distance from a center to a vertex. So here is the form of the polar equation of a conic with the focus at the pole. So now we're having polar graphs. So this is called the pole, remember? So a focus is at the pole, not a center. A focus is at the pole. The directrix is perpendicular to the polar axis, a distance p to the left of the pole. So here is what the polar equation looks like. It's r equals EP over 1 minus e cosine theta, where e is that eccentricity, which is c, little c, over a. Okay, so notice that we have cosine of theta because this graph is going to be symmetric about the polar axis, and we know that's true about the polar graphs with cosine in them. So let's look at how you do this analysis. So this one's kind of worked out for you. So let me write this equation over here so I have it handy. R equals EP over 1 minus E cosine theta. Okay, so the important features of this equation are the 1 has to be in this lower left corner. If that's not what you have there, you have to do some algebra to get it there. So this first problem just has R equals 3 over 4 minus 2 cosine theta. So we need to get a 1 down here. So we need to divide everything on the bottom by 4 or multiply it by 1/4. But the only way we can do that is to also multiply the top by 1/4. So that gives us 3/4 over 1 minus 1/2 cosine theta. And in this case, don't worry about having a complex fraction with a fraction and a fraction. It's actually important that it be in this form. So now you can see that the numerator is EP, and that's going to be the 3/4. Then look at the form. Here's the 1, here's the 1. Here's the cosine theta, here's the cosine theta. There's a minus in the equation. So E is this number 1/2 that's between the minus sign and the cosine theta. Well, if E is 1/2, substitute it in for E and solve for the P. So I'm going to multiply both sides by 2 and get that P is 3/2. So go back to the definition, and P is where the directrix is, a distance P to the left of the pole. So here's the pole. Here's a distance P equals 1.5 or 3/2 to the left of the pole. So this is the directrix. Then the pole is at a focus. So the focus is at the pole, the directrix is perpendicular to the polar axis, 3/2 units to the left of the pole. And then we can put a few points on here by doing an R theta graph. You don't have to do lots, but you should do at least 4. So if theta is 0, I put 0 into the equation. R equals 3 over 4 minus 2 cosine of 0. Well, the cosine of 0 is 1. 4 minus 2 is 2, so when theta is 0, I get R is 3/2. So this is the R is 3/2, theta is 0. This is the polar coordinates of this point. So this is a polar graph. Okay, so then let's do, that's 3/2. Let's do theta is pi over 2. So when theta is pi over 2, we'll get R equals 3 over 4 minus 2 cosine of pi over 2. Well, this is 0. So you're going to get 3/4. So here is the point. R is 3/4. Theta is pi over 2. So that's this point right here. And then you can see by symmetry that when I put 3 pi over 2, I get the cosine is 0 again, and so I'm going to get 3/4 again, so that gives me this point down here. So this is R is 3/4 when theta is 3 pi over 2. And then let's get one more point when theta is pi. Cosine of pi is -1. So I'm going to get that R is 1/2. So here is the point where theta is pi and R is 1/2 in polar coordinates. So then you can draw the shape and we can tell it's an ellipse. Let's go back here. It was an ellipse because the eccentricity is smaller than 1. So when the eccentricity is 1/2, which is smaller than 1, then we know it's an ellipse. And then you can verify your graph using a graphing utility. Okay, so if you have a polar equation of a conic with the focus at the pole and the directrix perpendicular to the polar axis, a distance p to the right of the pole, look at what's different. We end up with a plus in the formula. So you can tell whether the shape is going towards the left or towards the right by whether it has the plus or the minus, because it has to go away from the directrix. So this example again does not have a 1 in this lower left corner. So we're going to take 10 over 5 plus 4 cosine theta. And now I know I want a 1 here, so I'm going to multiply by 1/5 over 1/5. And I'm going to get r equals 2 over 1 plus 4/5 cosine theta. So now I can see that the numerator is EP. Whatever number is up there, that's EP. Whatever number is here between the plus and the cosine theta, so 4/5 is the E. So again, this is an ellipse because the E is smaller than 1. And then we're going to put E is 4/5 into this equation for EP to find the P. And P is going to be 5/2. Okay, so it's a distance P to the right of the pole, so 5/2, halfway to 5, 5/2. This is the directrix. So you know it's an ellipse because of the E. Focus is at the pole. Directrix is perpendicular to the polar axis, 5/2 to the right. And then you should plot some points again. So let's use the 10 over 5 plus 4 cosine theta and get some points. So let's do some r theta points where theta is 0. I'll have 10 over 5 plus 4, so 10/9. So when theta is 0, this point is at 10/9, comma 0, so a little past 1. When theta is pi over 2, I'm going to get that r is 2, because cosine of pi over 2 is 0. So this point would be r is 2 when theta is pi over 2. And we can see because of the cosine theta that we have this symmetry about the polar axis. So when we have the theta of 3 pi over 2, we're also going to get r is 2 away from the pole. And then let's also do pi. Now I have 10 over 5 plus 4 cosine of pi. Well, cosine of pi is -1. So you're going to get r is 10. So this point over here is r is 10 when theta is pi. So that's the polar coordinates of this point. And then you can draw the ellipse. So here are the 4 variations. We've gone through these 2 where the polar axis and the directrix are perpendicular. These 2 where you have sine theta, the directrix is parallel to the polar axis. And so, in fact, you have symmetry about the line theta equals pi over 2, which is what we know happens when your graph has sine theta in it. So this little chart will be on the exam so that you'll have it to refer to. So the part you need to be able to do is look at the equation, see that every one of these equations has a 1 at the lower left corner, so that's what you need to do. So if you have 12 over 4 plus 8 sine theta, you need to multiply by 1/4 over 1/4. So you get 3 over 1 plus 2 sine theta. Then 3 is your EP, 2 is your E. So E is bigger than 1, so that means you have a hyperbola. And then we plug in the 2 for the E in the